Alright, in this video we'll be continuing with alternating current, and in this video we'll be looking at what happens when we add an inductor into an AC circuit. So a lot of the things that we've learned when we apply capacitors into an AC circuit, we can apply to inductors in an AC circuit, okay? So I won't be going over some of the repeated content. If you want to look at that, you can look further up in the playlist, okay? So first things, I'm just going to draw out our circuit so we know what we're dealing with, okay? So we have our AC power supply, and then we have our inductor, all right? And because we know we're in AC, the current is going to be going back and forth. So just like resistors and just like capacitors, inductors also restrict the flow of current in an AC circuit, okay? So inductors resist flow of current in AC. And obviously, inductors don't resist the flow of current in the same way capacitors do, okay? It's going to be in a slightly different way. And just like in capacitors in an AC, we call this restriction of the flow of current the reactance of the inductor, okay? So the reactance of inductor. And remember, our reactance is the property of a component in AC that restricts the flow of current, okay? So property of a component in AC that restricts the flow of current, okay? So the way we denote the reactance of our inductor, we use an X, okay? Just like our capacitor, and then we put a little L to denote that this is the reactance of the inductor, okay? And our reactance of our inductor is directly proportional to the angular frequency, and the reactance of the inductor is also directly proportional to the inductance of the inductor. And so therefore we can say that the reactance of our inductor is equal to the angular frequency multiplied by the inductance. Okay, and if we remember, our angular frequency is equal to 2 pi f, or we can say 2 pi all over our period, okay? But this 2 pi f shows us that the reactance of the inductor is directly proportional to the frequency, okay? And so therefore, the higher the frequency, the higher the reactance of the inductor, okay? So the higher the frequency of our AC supply, the more the inductor is going to resist the flow of that AC current, okay? And if we think about it, this makes perfect sense. A high frequency means that the current will change direction often, okay? And so if it's changing direction often, we can denote this as a high rate of change. And if we remember the equation for our back EMF in an inductor, we have our back EMF is equal to negative L change in current all over change in time, okay? And our rate of change of current is our change in current all over the change in time, okay? And so if we have a high rate of change of current, we are therefore going to have a high back EMF. And if we remember, in our inductor, it is the back EMF which restricts the flow of current, right? And remember, that is because our back EMF is an opposing voltage, meaning it acts in the opposite direction to the supply voltage, okay? Okay, so that is the reactance. So now we can move on to the differences in phase between the current and the voltage across the inductor. Okay, so if we draw our graph like so, okay, and we have our voltage here and our negative voltage here, okay, and we have our voltage across our inductor looks something like this, okay, and so we can denote this as VL, okay. With an inductor in AC, the voltage leads the current by 90 degrees, or we could say that the current lags the voltage by 90 degrees, okay, either or. And so our current is going to look something like this, and so we can denote this as I. Okay, and so therefore we could say that the current lags the voltage across the inductor by 90 degrees. And just by merely looking at this picture, we can see how this makes perfect sense. If we look at these points right here, okay, this is when the rate of change of current is going to be the greatest, okay, because this is when the gradient of the graph is at its highest point, at these 3 points right here, okay. So if the rate of change of current is highest at these points, that means through our equation, this one right here, we should see that the voltage across the inductor, which is our back EMF, must be the greatest. And as you can see, at these exact times is when we have our greatest voltage across the inductor, okay? Similar thing in the other direction. If we were to look at these points right here, okay? Remember back to our calculus that this is when the graph has a gradient of 0 at these 2 points, okay? And so if the gradient is 0, that means the rate of change of current is also 0. And so therefore, we should expect a back EMF of 0 also due to this equation, because if this value is 0, that means this value must be 0, okay? And what do you know? We see right here that the voltage across the inductor is 0 at the exact same time. So if we compare this graph to the graph that I made in my RC video, okay, about RC circuits, we now know that in an RC circuit, the voltage across our resistor is in phase with the current. So we can almost just replace this with a current and the graph will look the exact same, okay? And so now you can see here, if we were to put these side by side, like so, you can see how the phase difference between the current and the voltage across our capacitor and the voltage across our inductor is opposite. In this scenario, our current lags by 90 degrees, okay? We can see we have a 90-degree lag here between our current and the voltage across our capacitor. However, in this scenario, the voltage across our inductor has a 90-degree lag to the current, okay? So in this scenario, our current is lagging our voltage across our capacitor. However, in this scenario, the voltage across the inductor is lagging the current by 90 degrees, okay? So you can see how the inductor and the capacitor are sort of opposites of each other. All right, that will be it for this video. See ya.